American Sign Language, or ASL, is a method of communication specifically designed so that people can communicate with the deaf community. The idea is simple. ASL signers make simple gestures with their hands so that people can communicate without having to speak. Due to the relative simplicity of the signs and the somewhat small amount of classes, 26, ASL classification has become a marquee task in the field of image processing and recognition. However, many ASL signers complain that signing can be a tedious task, especially when one is first learning how it works. The objective of this project is to implement an efficient method of signing words and sentences using ASL by creating a system that is similar to a phone keyboard's autocomplete function. This introduces our project, ASL Detection, Correction, and Completion, or ASL DCC. The ASL DCC application has three main submodules: the detection submodule, the natural language processing submodule, and the full stack Flask app submodule. Each of these three play a key part in the project. Here we show an example that we are all familiar with. As you are texting your friend, after each subsequent letter, you are given suggestions for how to finish the word you are on, making the experience of typing a less tedious task. We imagine that our application can be especially useful for situations where people want to communicate with the deaf community efficiently but don't have any interface like a keyboard or drawing tool.
So now I'm going to talk about the first part of this project, which is actually the detection submodel. To do so, we use the MediaPipe package from Python. So it allows you to detect landmarks on the end, so a certain position of different landmarks. So you get an X, Y, Z coordinate. So what we did with that is that we normalized those data based on the bounding box. How did we get this bounding box? We took the minimum and maximum X, Y, and Z coordinates, and then we had this bounding box that we could normalize. This is very interesting because it allows to be robust to different frame resolution and dimensions. The value also after were centralized around the middle of the bounding box, so the feature representation are independent of the end's locations. So it's again to be robust against the localization of the end in the picture. So then after we just created a simple model. It's a 5-layer convolutional network, and we use natural data points, and we got a pretty good accuracy. So we use natural data points per classes. So we have letters, symbols, for example, letters A, B, C. Symbols can be a delete, can be a space. And then you have also numbers to actually choose several suggestions later. So we confirm our results, and we had a very good accuracy, 98.2%, which is actually comparable to other ASL detection model from today. We also use another model, as we've seen in class, with YOLO v5. We didn't get very good results because actually the most important thing our model is MediaPipe, and thanks to that we could get a very high accuracy, and it's working pretty well. So here, using complex models just like YOLO v5 was not interesting. And the final output is just a single frame classification prediction. So based on the landmarks, you get a certain letter, A, B, C, for example, and then we fit that into an NLP submodel.
The NLP submodule is responsible for making inferences regarding the current output of the detection module. Depending on the state of the current prefix, the NLP algorithm will change its suggestions. For example, if the letter A was entered, the algorithm may output able as its first suggestion. However, if the next letter entered is P, then the NLP algorithm will change its first suggestion to apply, corresponding to the new AP prefix. The NLP submodule is built using a directed acyclical word graph, or DOG, which is a data structure that can efficiently and effectively find plausible words given an initial prefix. This DOG structure is similar to a probabilistic prefix tree. In the tree structure, all the descendants of a node have a common prefix, or parent node. The algorithm traverses the tree by reading in each letter of the currently typed prefix. It then creates a list of all the children nodes and sorts them by the corresponding frequency rates. The top 3 words are provided to the user as suggestions for auto-completion. To generate the corresponding frequencies used to sort the words, we process the Brown corpus and counted the occurrences of each word in it. The final part of the project was implementing a way to allow the signer to interact with the program in a user-friendly way. To do this, we created a mobile-friendly Flask web app.
The Flask app is a 4-step process that uses the previously mentioned submodules in conjunction with our website code in order to encapsulate the functionality of the entire project. An HTML video element shows the video stream and JavaScript code that utilizes the Canvas API to grab the frames from the video stream and deliver them to our Flask app via our WebSocket. That would mean that your phone, which is using our web app, would actually send those video frames to our backend and our Flask app for processing. So the Flask app gets these video frames in real time and buffers them so that they can be fed to our model in batches, and that way we have a more accurate prediction and use confidence scores when actually getting our outputs and giving higher accuracy. Now that we've discussed each component of the ASL DCC, let's look at the completed prototype. As you can see, we can easily sign complex words and phrases using less time than any other application with similar purposes. Our autocomplete and auto-revision algorithms work well in conjunction with efficient detection models and are compatible with mobile and embedded devices.
While we think this application has true potential with the ASL crowd that sign letters, we acknowledge that our project does not address the more popular method of signing, full words. Full words are signed by moving gestures with both hands. Okay? Our model would not generalize to this application for two main reasons. First, the obvious reason being that we did not train our algorithm on these types of signs. Secondly, and the more pressing issue, is that our model fails to account for motion. If we wanted to implement sign words, we would need to utilize an LSTM network to account for past frames and accurately detect words and display sentence completion phrases. This is where there's a lot of space in this field, but we think that we laid out a good groundwork with this project.